Yeah, we couldn't get quite 7 minutes, but I guess 5 minutes also have to do. Okay, so first I wanted to fix some notation, but I guess there are many people here familiar with tropical geometry. One important thing is I usually talk about tropical projective space and say like TPN or something. And usually it's like one coordinate more than you would expect. So just as a reminder, I have this real numbers with an infinity. I removed all infinity vectors. I quotient those by the all ones vector. Okay. And now I want to switch this around. So yeah, last minute change. Right, so I'm talking about polytropes, but they are a special class of tropical polytopes. So what is a tropical polytope? Here are 3 examples of those in the tropical projective plane. And the last 2 are polytropes, and the first one isn't, because those 2 are also classically convex. Because you can see here there's this antenna sticking out at the upper left corner. Okay, now we can go back. And the specific type of tropical polytopes or polytropes that I want to look at come from weighted graphs. So I have an adjacency matrix. And for my specific motivation, I even have like acyclic graphs. So this means I have a topological ordering. I can order everything around, so I have these low triangular matrices. And in particular, I have many infinities up there. Okay. And what I wanted to do is look at the combinatorics of this. So I first have to determine what gives me the tropical combinatorics of my tropical polytopes. And there are 2 points of view. Since I have this weighted digraph perspective, I can look at classical hyperplanes, cutting out my tropical polytope. And they are given up by these xi minus xj lesser equal than cij. These would be the half spaces, so I have just like these hyperplanes themselves, and then I have the special set inside there. Of course, there are also tropical hyperplanes, which would then be given by the coordinates of the points. And for every point, I have a tropical hyperplane. So this would be one, this would be one. I mean, of course, in this case, this doesn't come from a cyclic graph because they are bounded. Okay. And coming back to this example with like this phenode graph, there are 2 possible polytropes that I can get out of this. So either the weight corresponding to the 1 to 3 edge is smaller than the detour around, then I get something that looks like this. But as soon as I push this hyperplane further up, so if I increase this weight, at some point it will be above this vertex here, and then I get this ice cream cone. So you can here see the hyperplanes, and you see at this point, from this point on, it becomes redundant. And this also reflects in the graph. So I was asking myself, how much of the matrix, of the weight matrix can we recover if we just see these shapes here? And the result is that I came up with something that I call the weighted transitive reduction. Yeah, you can kind of think of those as covering relations if you think of the graph as some kind of coset. But they take into account the weights. So basically what I'm saying, I have this weighted transitive reduction, and I keep an edge with the same weight if this edge is already the unique shortest path from source node to target node. If it's not, then I just throw it out, because I can replace this direct edge by some other path. And then the theorem is, if I have a matrix coming from an acyclic graph, then this weighted transitive reduction describes a non-redundant set of inequalities. So in particular, this is the stuff that I can recover from seeing the polytrope. And the other thing is, I wanted to enumerate them. So how many tropical combinatorial types of polytropes can we get from these directed acyclic graphs on our nodes? And there's a theorem by Alex and Philippe Rincon, where they say we have a bijection between combinatorial types of arrangements of tropic hyperplanes and projective space, and regular subdivisions of subpolytopes of this product of simplices. But this is for tropical polytopes, so for these complexes that we have. So then I noticed that the polytrope itself also, the polytrope appears in this complex, and this is a subpolytope. And in particular, it corresponds to a very specific vertex in this product of simplices. So we have a subdivision of this subpolytope of product of simplex, and then you take a vertex figure inside there, so even a small thing. And this basically comes from this perspective as a weight digraph polyhedron, which we can also like express tropically. And then I was using this stuff here to look at the parameter space, for example, in the case of tropical projective plane. And then I noticed that if we check for which choice of parameters we get which polytrope, we get, for example, this open cell here corresponding to this graph. So I'm just drawing the weighted transitive reductions. We get this open cell. Sorry, this is wrong. So this line corresponds to blue cell. We have this thing here, we have this thing here, corresponding to this graph. And then we have this one corresponding to this thing. And I'm missing a color. So the last one corresponds to having this graph. And looking at this weighted transitive reduction gives me this decomposition of the parameter space for this triangle graph, for example. And you see it's like a somewhat weird polyhedral complex. So this one is not really polyhedral complex, but if you then look at if you then compute the actual tropical vertices, you will see that this map would collapse, for example, this cell to this line here, to this blue line, and then you would at least get a polyhedral complex. So when we calculate the tropical vertices, parameter space would look like this. Almost.